Okay. So today we're going to look at related rates. So if we can turn to page 9. So yesterday we did implicit differentiation, right? And implicit was where we had to do something with a y variable because it was a dependent variable. So we had to attach a dy dx for every y variable that we found the derivative for. So if it was like 3y squared, we would do 6y and then dy dx, right? We have to keep track of our y variable. With related rates, we are going to have a similar process as implicit. It's just that now our independent variable is no longer x. Now it's going to be time. So everything is no longer going to be d over dx. It's going to be d over dt. And also, it is going to impact every variable, not just y. So it could impact x, v for volume, s for surface area, theta for angle measure. Every variable is going to get impacted by time. So with related rates, these are problems where we relate the rate of change of a dependent variable, right, such as basically any variable that we have in the problem, with the rate of change of an independent variable, which is time t. And a lot of times, time t will be invisible from the equation that we're going to build. It's only going to show up as we find the derivative. Right, so here are the steps. We're going to identify the equation that relates to the variables. Right, so example, could be a Pythagorean theorem problem, which is a common one. Could be a volume problem, could be surface area, could be a trig equation problem. Also, there are some similar triangle problems that are a bit more involved, such as cones and shadow problems. We'll look at a cone problem on this page later. Okay, so we identify the equation first, and next, we find the derivative of each variable with respect to time t. So every variable, we just go ahead and find the derivative, but as soon as we find the derivative, we're going to attach a d over dt for that variable. So it could be a dx dt, could be dv dt, could be ds dt, right? Just depending on whichever variable we're working with. Next up, we're going to solve for the variable in the new derivative equation. Okay, let's start off with the most common, the basic one that we did at the very beginning of our related rates unit, which is a triangle problem, which is a ladder problem. Okay, so number one, it says a 15-foot ladder is sliding down a building at a constant rate of 2 feet per minute. Okay, how fast is the base of the ladder moving away from the building when the base of the ladder is 9 feet from the building? So let's go ahead and draw our triangle here. So the base of the triangle represents the ground, the height of the triangle represents the wall, and then the hypotenuse of the triangle is represented by our ladder. Okay. Our ladder is sliding down, so it's going to move in this direction, and it's going to be moving away from the wall. Okay. We know that we're working with Pythagorean theorem here. Size of a triangle, so we know we're working with x squared plus y squared equals z squared. Let's go ahead and find the derivative of each variable, but each time we find the derivative, we're going to attach a d over dt for that variable. So x squared becomes what? 2x But we need to attach what? Times dx dt, okay? Y squared becomes 2y, yep, dy dt. And same thing on the other side, 2z dc dt. So we see this is helpful because we know that there's going to be 6 variables involved. We have to account for each of the 6 variables, and then hopefully we can identify 5 of them and then solve for that 6th one. Okay, let's see what we have. Let me list out all the variables here. All right, 15-foot ladder. Which variable is that? Z, yep. Is sliding down a building at a constant rate of 2 feet per minute. Sliding down 2 feet per minute. What do you think that is referring to? dy dt, okay? Because we see that as the ladder slides down, it's impacting the height of the triangle. Any adjustment that we have to make with that 2 feet per minute? Negative, okay. And why is it negative? Okay, down is really not the issue. What's happening to the height? Shrinking. Okay, so that's what's important. Okay, I want us to make sure that a lot of times down can mean something is shrinking, but not all the time, right? So we want to make sure that we don't base our decision from the direction of movement. Base your decision on what's happening to the height you're referring to, or that value you're referring to. If that you can imagine that value decreasing, then you want that rate to be negative. If you can imagine that value increasing, then you want that rate to be positive. Okay. And also another hint is that you see the word per minute. You know that anytime that has time involvement or movement involvement, it has to be a d over dt. It's not going to be a static value. Okay, how fast is the base of the ladder moving away from the building? Okay, how fast is the base of the ladder moving? What are we looking for? dx dt, right? Base of the ladder moving. You know the base is referring to x. Movement will be dx dt. Yeah. Okay. When the base of the ladder is 9 feet from the building. What's that 9 referring to? X. Okay. Okay, we have the missing variable that we're looking for, but we want to identify all 5 of these before we can. Otherwise, we can't solve for this equation if we have too many missing variables. Okay, so how can I find this y here? Yeah, Pythagorean theorem, right? Yeah, because I have a squared plus b squared equals c squared. I have 2 sides of a right triangle. I can find that third missing side. This is going to be a variation of a 3, 4, 5 triangle. So you can also use your calculator. This will end up being 12. Okay, the other missing piece is this dz dt. Okay, what do you think dz dt is going to be? Yeah.
You could do.
Okay, think about the ladder. It's not changing, right? This ladder will be 15 feet at the beginning of the problem. It'll be 15 feet at the end of the problem. So therefore, the rate of change of that ladder is what? 0. Okay. Okay, we have everything that we need. We have our equation. We have all of the variables accounted for. We can just insert and solve for dx dt. Okay, let's try that. Okay, we should have gotten 8/3 feet per minute. X is in terms of feet, time is in terms of minutes. So if we just look at the units involved, we can build our unit for this variable. Now we're getting a positive value. Is that matching with what we imagine in our diagram? Yes, right. 8/3 is positive, meaning that the base of this triangle is increasing at a rate of 8/3 feet per minute. And the reason that's increasing is because the ladder is sliding away. As the ladder is sliding away, we can expect this base to get larger and larger. All right, any questions with one? Okay, let's look at number 2. A beach ball is deflating at a constant rate of 10 cubic centimeters per second when the volume of the ball is 256/3 pi cubic centimeters. What is the rate of change of the surface area? We have our surface area equation for a sphere. We have our volume equation for a sphere. Let's gather some information here, though. Beach ball is deflating at a constant rate of 10 cubic centimeters per second. What do you think this is referring to? Which variable is this referring to? Yeah, so cubic centimeters, you know that's volume, that's 3-dimensional unit. Per second, there's time involvement there, so you know it can't just be V, it has to be dV/dt. Okay. All right, any other adjustment that we need to make with that 10? Negative, right, deflating, so we know that this beach ball is decreasing at a rate of 10 cubic centimeters per second, so -10. When the volume of the ball is 256/3 pi, so that's information that's pretty straightforward. Let's go ahead and write that down. What is the rate of change of the surface area? What are we looking for? ds dt, right? You see the word rate, so you know it has to be not a static value. There's a rate, there's a motion involved. So ds dt. All right, let's go ahead and build our derivatives because we know we need our derivatives in order to access ds dt and dv dt, right? So we'll start with v. Okay, we find our derivative, v becomes just dv dt, right? Okay, the only variable here in this equation is v and r. Pi is not a variable, pi is just a coefficient. So 4/3 pi isn't going anywhere, it'll just hang out in front. And what does r cubed turn into? Yes, yeah, so I'm going to say 3r squared, which, yes, you're right, the 3's will cancel out. But we need to include also what? DRDT, yeah, every variable impacted by time. All right, 3's cancel out, 4 pi r squared. And we'll come back to that when we need it. All right, let's work with our surface area equation. We'll go ahead and find their derivatives, or find this equation's derivative. Okay, S becomes ds dt. Every variable has a time component, at least derivative-wise. Okay, 4 pi does not go anywhere. That's just a coefficient. It's the r squared that we're looking to change. What's r squared turn into? To r and dr dt. Do a little bit of cleanup. All right, everything that we need is in front of us. Let's see what our end goal is. We're trying to find DSDT. So ideally, we would just we're given R and DRDT, we can just plug in and solve, but we don't have R and we don't have DRDT, at least not directly, right? If we did, it'll be quick and easy. But maybe the DVDT and V could be helpful in helping us find these missing variables that we need. So let me ask you, how can this volume information help us out? Yeah, we can involve the volume equation, right? We have the volume value, involve the volume equation. We can see ourselves solving for R, and that can help us get a piece of the variable information that we need. Good, so that's what we can work towards. And how can DVDT help us? We're good. We have a DVDT equation, we have a DVDT value, and assuming that we already found R, we can also insert R and we can find DRDT. If we have DRDT, then we have those two missing pieces that we need to get to our value. Okay, so let's work with our volume equation to try to get to R. So here, the 3's can cancel out, the pi's can cancel out. We're able to make progress towards solving for R. Divide both sides by 4. $256 divided by 4 is 64. Take the cube root. Okay, so that's useful information that we're going to need. Right, let's move on to DVDT. We know DVDT is going to help us out to help us find that DRDT that we're needing at the end. So I'm using this and this to help me find that last missing variable that I need, that DRDT. Oops, sorry. Okay, that's right. So R, I should replace R with 4. Okay, let me do that again. This gives me 64, divide both sides by 64 pi. Now we can do a little bit of reducing here. 10 to 64 can reduce to be 5 over 32, but careful, this pi is going to stay in the denominator. Okay, we can't just let that pi float up to the top. It's not going to mean the same thing. So DRDT. All right, so these are the two missing pieces that we need, right? We have R, we have DRDT, and now we can look to find DSDT. Eight times 4 is 32. 32 and 32 will reduce because one's in the numerator, the other's in the denominator. The pi will also reduce. So the only thing left is that -5, right? All right, our units of measure. what's it going to be? Surface area is what? Centimeters squared, right? Surface area is two-dimensional over per second. Yeah. Yeah. Okay, any questions with 2? All right, take a look at number 3. This is number 3 is similar triangle problem, which is I think the most time intensive in terms of related rates problems, because we have to go through cones involved. We got to keep track of 2 variables. We got to do similar triangles, and there's a lot of algebraic steps. So let me go through this slowly here. All right, water is poured into a conical container at a rate of 10 cubic centimeters per second. The cone points directly down, and it has a height of 30 centimeters and the base radius of 10 centimeters. How fast is the water level rising when the water is 4 centimeters deep? So let's draw the diagram here. We have a cone that points down. Radius is 10. Height is 30. And then there's also water level that's changing inside that tank. Water, we have a container that water is poured into at a rate of 10 cubic centimeters per second. What do you think this is referring to? Which variable is that? DVDT, positive or negative? Positive is poured into, right? You know that the volume is increasing in that container. So put that to the side here, DVDT. How fast is the water level rising? Okay. What are we looking for? Which variable and which water level rising? That's referring to what? Change in height. So which variable is that? DHDT. When the water is 4 centimeters deep. What is 4 referring to? The height, okay. All right, put a box around this value. This is a cause for a lot of mistakes here. What we want to make sure that we do is we don't want to touch this, okay? Do not use until end of problem. The temptation is that you're going to see H's as you build your similar triangle. The temptation is you want to start using that 4 a little earlier than you're supposed to, and that's just going to throw everything off. You're not able to hold on to that H variable, and then you're not able to get the equation to be what's supposed to be. So we're going to use this 4, but not until all the calculus is done. Okay, at the very end, when we're ready to start plugging information in, then we use the 4, but we don't want to use this 4 at all at the beginning of this problem. Okay, so we're going to go ahead and create our kind of just a slice of this 2-dimensional version of just that triangle within a triangle. Because our issue is that we have too many variables, R, H, and V, and not enough information. So we want to go through similar triangles in the hopes of replacing one variable in terms of the other if we can find a relationship in terms of their values. So let me draw this triangle within a triangle. Here's the container with a radius of 10 and a height of 30. And then there's also the water level inside the tank. But we know that as water is getting poured in, we're expecting that radius to be changing of the water level. And we're also expecting the height of the water level to be changing, right? So the water inside the container is also going to take on the shape of a cone. And we're just looking at the fact that we're just going to looking at a right triangle slice of that three-dimensional problem. Okay. We're going to create a relationship here using proportions. So we can say the radius of the cone is to the small radius is to the big radius, as the height of the small cone is to the height of the large cone. Cross multiply. And now the next decision we have to make is, do we solve for R or do we solve for H? So here's the hint. The hint is that you look at what we're looking for. We're looking for DHDT and look at the information that we're given, H. We want to, easier way is if I have H's in my equation, then I'm going to naturally be able to get to this information a little faster. So what that is telling us is things will move a lot faster if we're able to remove the variable that's not part of what's given to us. I mean, we can solve for R, it just will take a little bit longer, an extra 1 or 2 steps to get to the answer. So we want to try to find the most efficient way to our answer. So the most efficient way is if I can get radius to disappear, then everything will be in terms of H, and all this information will just naturally show up a lot faster for us. So I'm going to solve for R because I want the R to be replaced. Divide by 30. 10 over 30 is 1/3. R is equal to H over 3. So let's go to our original volume equation now. And we're going to make a substitution. H over 3 in for R. That way we can get our volume equation purely in terms of H. Gives us a faster path towards our answer. All right, let's clean this up. Okay, eventually, we want to get to the point where we can just do power rule, but we don't want to do any calculus just yet. We want to try to clean everything up so that our calculus step will be easier. So I'm going to square the H, square the 3, and try to put all the coefficients together and put all the variables together. Three times 9 is 27, pi over 27. H squared times H is H cubed. So now we're ready for our derivative. Okay. V becomes DVDT. Pi over 27 is not going anywhere. It's just going to hang out in front. H cubed becomes what? 3h squared, right? 3h squared, and then d. What else do we need? Yeah, to get DHDT. Okay. now that we have the derivative in front of us, okay, now everything that we've gathered from the beginning can be used. Okay, we can replace 10 in for DVDT, replace 4 in for H, and that will cleanly allow us to solve for that missing piece that we need, DHDT. Okay. Three over 27 is 1/9. I got that 16 there as well. Dividing by the 16 pi over 9 is the same thing as multiplying by the reciprocal. So I'm just going to multiply by the reciprocal to move it over and get that DHDT by itself. Ten and 16 can cancel and reduce to be 5 over 8. So 45 over 8 pi. Again, that pi is going to stay in the denominator. We can't just make it come up to the top, even though it looks like it's more correct. Algebraically, that's where it belongs. Okay. And what's our unit of measure? Centimeters per second. Okay. Okay, any questions here? All right, now towards the end of the semester, we also did a trig unit, and within the trig unit, we also did related rates. So I want to go through a specific trig problem, a related rates problem that involves trig here. Related rates problem involving trig. So let's look at number 4. So the right triangle shown, the angle theta is increasing at a constant rate of 2 radians per hour. At what rate is the side of length x increasing when x is 4 feet? All right, let's go ahead and gather some information here. It says the angle theta is increasing at a constant rate of 2 radians per hour. All right, which variable can we assign that 2 radians per hour? D theta dt. Positive or negative for the 2? Because increasing, yeah. So we're looking at those words to kind of help us decide how to assign this the plus or minus of the rate. At what rate is the length x increasing? What are we looking for? The x, right? dx dt. At what rate is the side length x? You know that's not a static value, that's a rate. So dx dt is what we're after when x is 4 feet. Okay, so anytime there's theta involved, we're going to have to go through trig. So either sine, cosine, or tangent. And we want to look at the diagram, and we want to be able to choose sine, cosine, or tangent depending on which trig equation is going to hit all the values that we want. So between sine, cosine, and tangent, which will allow us to hit the theta, the x, and the 5. Sine, because sine is opposite over hypotenuse. Okay, so from here, we want to find the derivative, but before we find the derivative, just so that the right side can look a little bit easier, so we're not having to think about quotient rule, which we don't need. Let's just push that 5 out in front as 1/5. Visually, it just makes it easier, I think, for our calculus process. It looks a lot easier in here as a power rule problem, right? Okay, so let's find the derivative. Remember, time is also involved here. So sine theta becomes what? What's sine's derivative? Yep, cosine theta. Anything else? D theta dt. Okay. What does 1/5 x turn into? Good. 1/5 stays, x goes to 1, but we still need to attach that dx dt. Okay, thanks. Okay, so let's look here. We're trying to solve for dx dt, so we see that there. We have d theta dt, that's good. We can insert that. But now the question is, what to do with this cosine and what to do with this theta? So the thing we have to make sure that we understand is that we're not going to do anything with theta, okay? In fact, we're not going to even know what theta is. But what we can do is we can make a substitution for this entire trig cosine theta. We're going to find the ratio associated with that cosine theta. To do that, we're going to create a second triangle, and the second triangle is going to help us allow us to find that ratio that we need. We can insert for this moment in time. So here's my second triangle. Five. Let's see if we can fill out the rest of the triangle. What information do we have about this triangle at this moment in time? X is 4, right? So X is 4. And if this side is 4, how can I find this missing side? Yeah, so Pythagorean theorem. This is a 3, 4, 5 right triangle. So based off of this triangle at this moment in time, what do you know about what's cosine of theta? 3 over 5. Now we have everything that we need. All right, so this is the additional step that is unique for these related rates problem. Okay, it's only specific for trig. The other problems we don't experience this additional step. All right, so let's make our substitution here. Cosine theta gets replaced with 3/5. D theta dt is 2, and then our dx dt is what we're looking for. Six fifths, I can multiply both sides by 5. Right, dividing by 1/5, the same thing as multiplying by 5 over 1. Fives cancel out. Dx dt is just 6. And what's the unit of measure? Good. X is feet, time is hour, so feet per hour. Okay, one more problem I want us to do together is page 11, number 2. Okay, does anybody still need this page? Page 11, number 2. I want to go over this problem because cones and cylinders they have very similar formula, but I want to help convince you that cylinders are a lot easier than cones. Okay, a lot easier. So what I want to make sure also is that we don't try to apply the steps for cones with cylinders. Okay, it doesn't work that way because of the way that's shaped. But I'll go over that in detail. So it says a cylindrical tank with a radius of 5 feet is being filled with water at a rate of 3 cubic centimeters per minute. How fast is the height of the water increasing? So let me draw the diagram here. Here's my cylinder. There's my container. Radius of that container is 5 centimeters. Filled with water, so we know the water is going to be filling up in the tank. Okay, so water is being filled at a rate of 3 cubic centimeters per minute. What variable is that referring to? Good. DVDT, positive or negative? Positive. You see the word being filled, so you know that the volume is increasing. How fast is the height of the water increasing? What are we looking for there? DHDT. Now, let's think about what's happening to this water level. Okay, so as the water is rising, is the height changing? Yes. Okay, so that's consistent with what we saw with cones. As the water level is increasing, is the radius of the water level changing? No. So that tells us that there's no need to hold on to this radius variable if it's not going to change at all throughout the entire problem. Now, if you look at cones here, cones was a little bit more complicated because as water level is rising, radius is changing and the height is changing. We can't just replace a value into that variable because it's not going to stay the same throughout the entire problem. So that's why we had to go through an additional step to hold on to those variables and solve one in terms of the other, and then plug in because of the fact that we have more moving parts in this problem than we do in this problem. So this tells us that even though the formula looks very much the same, we can simplify this because we can just completely rid ourselves of the radius variable from the get-go, from the beginning. Because there's no need to hold on to a variable if it's not going to change at all throughout the entire problem. It'll stay 5 the entire way through. So if I rewrite this equation here, b is equal to pi 5 squared h. Notice the radius is completely out. 5 squared is 25. And now we can jump directly to our calculus step because we don't have to worry about dealing with that second variable, r. So no need for similar right triangles. I see some students, they get so used to the cone problem that they want to apply similar right triangles for cylinders, and it's just not going to work. Okay, it's easier, but it's also different. So that's something that I want to make sure we're understanding there. So let's jump into our derivative step. V becomes 25 pi is going to stay. That's just the coefficient. H becomes dHdt. And we're almost there, right? dVdt, we can replace with 3, and then we can solve for our missing variable dHdt. Divide both sides by 25 pi. Again, that pi is going to stay in the denominator, so we got to leave it there. We can't move it up to the top. And what's our unit of measure here? Okay, your homework is going to be a little abbreviated. I just want us to just do related rates tonight. So just number 1 and 7 on page 11 and 12. I'll send out a reminder. Okay, tomorrow we'll focus on theorems, but tonight you will just practice with related rates. So just numbers 1 and 7 on page 11 and 12.
I'll show you my homework.
Okay.
It was 5 through 7, right?
5 through 8. Yeah.
Oh, 5 through 8.
Okay, thank you.